Do you see my screen now?
Yes, yes. And if you move your cursor, your pointer, yeah, we can see that also. Okay, good.
Okay.
So you may chair yourself now.
Okay.
This is a self-service conference.
Okay. So I will give a talk on chiral massive news, null boundary symmetries in topologically massive gravity. This work has been done in collaboration with Shahin, Vahid, Hussein, and Selim. Actually, this work is continuation of ongoing project with Daniel Grumiller, Saeed Sadarian, Shahin, and Vahid, and Hussein, and Selim. The motivation is in fact, this fact that black hole horizon is a null surface, and hence we study symmetry near null surfaces. And another motivation is the existence of an infinite number of surface shards carried by black holes give rise to new exciting development in the understanding of black hole information and systematic treatment of boundary degrees of freedom and their interaction with bulk degrees of freedom in the second order formalism. And the end of such research would be to provide an accurate set of all macrostates for semi-classical black holes during consequences on the evaporation of black holes and the avoidance of information loss. As Shahin said in his talk, in pure gravity, indeed, the d dimensions, the number of independent components of G mu nu is d times d plus 1 over 2. And the number of bulk propagating degrees of freedom is simply d times d minus 3 over 2. And the number of diffeomorphisms is d. Therefore, the number of boundary degrees of freedom is d. In pure gravity, in 3 dimensions, the number of boundary degrees of freedom is 3, and there is no propagating degrees of freedom. To add bulk propagating degrees of freedom, we have to consider another models in 3D gravity, and topological massive gravity is one of such examples. In fact, in 3 dimensions, metric has 6 components. 3 of them can be fixed by diffeomorphisms, and hence there remain 3 independent functions over the space-times. And equations of motion describing TMG order partial differential equations. Therefore, solutions of this theory will be uniquely determined when 9 codimension 1 functions are specified on the boundary. On the other hand, canonical analysis of topological massive gravity implies that, contrary to Einstein gravity, there are 4 second-class constraints in addition to 3 first-class constraints. And hence, we expect that 5 of these codimension 1 functions can be determined in terms of the other 4 codimension 1 functions via constraint equations. Therefore, solution space near null surface, which is located at r equal to 0, can be uniquely determined as there are 4 codimension 1 functions. 3 of them are, in fact, boundary degrees of freedom, and one of them is related to bulk propagating degree of freedom. The outline of my talk is as follows. I will give a short review of topological massive gravity and its surface charges. I will explain null boundary symmetries and surface charges. I will introduce fundamental slicing and partially fixing Y term in this context, and I will show how change of slicing on solution space plus fixing Y ambiguity can render charge to be integrable. And the main results are as follows. The solution phase space is described by 4 independent functions on null cylinder. 3 of them are boundary degrees of freedom, and the third one, the fourth one describes chiral massive graviton which propagates in bulk. I will consider vanishing cotton tensor solution phase space where there is no propagating degrees of freedom and surface charges are integrable there. Also, in non-vanishing cotton tensor solution phase space, there is a non-zero flux due to massive gravitons passing through the null boundary, and one of surface charges are non-integrable. And there is a fundamental slicing using or together with an appropriate choice of Y term in which the charge algebra is simply Heisenberg plus Virasoro. The action describing TMG is given by this equation, where Lagrangian is given by this equation, where first 2 terms are first 2 terms describe pure Einstein gravity with negative cosmological constant, and the last term is gravitational Chern-Simons term. Also, 1 over mu is the Chern-Simons coupling constant. Despite the fact that metric is a covariant quantity under diffeomorphisms, I mean, it obeys this equation, but the metric connection is not because of the this term, because this term appears in this equation. I mean, the variation induced by diffeomorphism is not equal to its lead derivative along the diffeomorphism generator vector field. Because Chern-Simons term is constructed out of metric connection and its derivative, therefore TMG Lagrangian is not diffeomorphism invariant. Let's consider a first order variation of Lagrangian, which can be written in this form, where E mu nu is equation, E mu nu equal to 0 are equations of motion, where G is Einstein tensor and C mu nu is Croton tensor. In the first order variation, symplectic potential, and it is given by this formula. Also, the definition of a symplectic potential is ambiguous, and this equation only determines symplectic potential up to adding a term like this, where y mu nu is stiff symmetric with respect to mu and nu indices. Also, equations of motion can be written in this form, where curly T is defined by this equation, and the mu nu is a tensor valued operator. On shell, one can show that curly T is traceless and transverse, and hence we deduce that information about massive propagating mode is encoded in curly T mu nu. And equations of motion are covariant. And one can show that variation of the Lagrangian density induced by diffeomorphism generated by vector field Kc is given by this equation. In fact, despite the fact that Lagrangian of describing the TMG is not invariant under finite diffeomorphism, but it is invariant under infinitesimal diffeomorphisms. And therefore, we can define surface charges in this theory too. In this equation, capital C encodes the non-covariant part of Lagrangian. Also, one can check that symplectic potential is not a covariant vector, and because this term appears in this equation. We use covariant phase space method to compute charges in TMG model. In order to do so, we define Lewald symplectic current by this equation, which is conserved on shell, and hence we can define surface charge variation associated to the vector field Kc by this equation, where sigma denotes a Cauchy slice and d sigma is its boundary. This definition has two parts. The first part is contribution of Einstein-Hilbert term in the Lagrangian, and the second part is contribution of Chern-Simons gravitational term. As I said before, one can shift Leibniz symplectic potential as this equation. And this is the only ambiguity in definition of symplectic potential that can affect the expression for charge variation. And as we will see later, fixing this ambiguity is crucial part of charge analysis for the TMG theory. Despite the diffeomorphism non-invariance of the TMG action, the charge variation is covariant, and adding Y term does not affect this fact. To consider near null boundary metric, we have to introduce an appropriate coordinate system. To this end, we take V to be light cone time, our radial coordinate phi transfer direction, 2 pi period, and we denote the null surface by curly n, which is located at r equal to 0. Near null surface, the metric takes this form, and we assume the Taylor expandability of metric, then we can expand functions that appeared in metric around r equal to 0, and it is clear that the induced geometry on n can be read as this equation, this line element. For later convenience, it is we in fact introduce two null vector fields L and N. L is an outward pointing vector field, and N is inward pointing. Therefore, we can decompose metric into 3 parts, where Q mu nu is induced metric on the null boundary. For later convenience, we define TLL, TL phi, and T phi phi. Some relevant quantities to describe the near horizon symmetries are expansion of vector field L and expansion of vector field M, and a twist field, which is defined by this equation. And because L is a generator of the null surface, we can define non-affinity via this equation, where kappa is non-affinity of geodesics generated by L, and hence our configuration space, the number of codimension 1 fields on configuration space is 7, and I will show them collectively by 5. The vector field KC in this form, which is given by this form, preserves the R equal to 0 null surface and metric expansion around the given surface. where TW and Y are codimension one functions. Because our vector fields are state dependent, then we have to use adjusted brackets to compute the algebra among them. And hence we show that this algebra closes. In fact, this algebra is a diff C2 plus while C2 algebra, where C2 is a cylinder is spanned by V and phi. T and Y generate diffeomorphisms on the cylinder, and W generates while scaling along the radial direction. And this is a quite geometric result, and it is independent of the theory. Now, let's consider non-vanishing Cotton tensor solution phase space. So we consider first equations of motion to the lowest order in R. The trace part determines V2 in metric, and the LL component of equations of motions determines the non-affinity, and the L phi component determines the angular velocity aspect of null surface. Then the non-vanishing Cotton tensor solution phase space is described by 4 independent functions of V and phi. 3 of them, namely omega, epsilon, and eta, are parameterizing the boundary degrees of the solution space, and the last one, let's say tau, or curly TLL, in them associated with the massive chiral graviton. The density of surface charge variation for TMG model can be written as this equation. For vanishing Cotton tensor solutions for which T mu nu is equal to 0, do not have a local propagating degree of freedom. Therefore, we expect that there should be a slicing on the solution phase space where a charge become integrable. However, in TMG, change of slicing does not render charge integrable. But we can solve this problem by recalling Y ambiguity. We can fix Y ambiguity partially to render charge integrable. So we first introduce change of slicing as these 3 equations. I mean, we define Y tilde, W tilde, and T tilde. And we also consider a Y ambiguity term like this, where B lambda is given by this equation. Null boundary symmetry algebra in this new slicing, which I will call it tilde slicing, is in fact A2 plus with algebra. With part is generated by y tilde, and A2 denotes local U1 plus U1 algebra on the null cylinder and is generated by T tilde and W tilde. Therefore, the charge variation in tilde slicing can be written as this equation, where S and J and P are defined by these equations. The three first terms can be integrated, but the last term seems that we cannot integrate it, that part. In fact, in this charge variation, last term shows that we can interpret the last term as a flux term, and this flux is through the null surface because the L generator of a null surface is perpendicular to M, and we can write killing vectors by this equation. Also, this flux is proportional to Ricci curvature along the null surface, and the surface charge is integrable. The surface charge is integrable for a vanishing point, because in that case, curly T is equal to 0 and this term will drop. And in the tilde slicing, we assume that W tilde, Y tilde, and T tilde are state independent. Therefore, we can integrate charge variation in vanishing cotton tensor case. To create the non-integrable charge, like what we have here, we use Barnish-Torsart modified bracket method. In that sense, we split charge variation into integrable part, which is denoted by Qi, and non-integrable part F. And the non-integrable part is associated to flux. The transformation laws for S, P, and J are given by these three equations. The appearance of T tilde and W tilde shows that S and P form, in fact, the Heisenberg algebra, and these three terms written in red show that J itself form Virasoro algebra. Using the definition of modified bracket, we can show that the modified bracket of integrable part of the charge is given by this equation, where K is the field independent central extension term. In the tilde slicing, the S and P form Heisenberg algebra, and J itself formed Virasoro algebra, and therefore the algebra among charts become a direct sum of Heisenberg and Virasoro algebra. In terms of Fourier modes, and after quantizing the charts, we can show that the algebra among Fourier modes are given by these equations, where Sn is entropy aspect charge, Pn is expansion aspect charge, and Jn is angular momentum aspect charge. So let me add a few more comments on this algebra. As we can see here, these Fourier modes are functions of V. Zero mode of S, namely S0 is equal to, or it is proportional to Wald entropy. P0 is proportional to logarithm of expansion of a null vector field generating the null boundary, and J0 is the angular momentum charge. And it is clear that structure constant in the algebra are V independent. There are two kinds of central terms in our case. One is H equal to 1 over 8G, which appears in the Heisenberg part and is mu independent. And in fact, it is what we had in our 3D example, in pure gravity example in 3 dimensions, which was explained by Jose. And the other appears in Chern-Simons model, which is C equal to 3 over mu G. And the central term in the Virasoro algebra, I mean this C, is coming from gravitational anomaly in the Persian dual to the CFT. With Brown-Henry boundary condition, one can show that there are two central charges in in the TNG model, let's say C left and C right. And what we have here is a difference between them. The light quantum coordinate V is not among the generators of tilde slicing, because d by dv is field dependent in the tilde slicing, as you can see here. But instead, we can introduce another appropriate time coordinate v tilde, which is more closely related to the tilde slicing by setting t tilde is equal to 1 and w tilde and y tilde equal to 0. Therefore, we can write generalized charge conservation in this form. Now we consider vanishing proton tensor solution phase space in which proton tensor vanishes, and hence curvature mu should also vanish. Equations of motion are simply H.Adami equation Dommer equation and T phi phi equal to 0. These equations of motion restrict the family of near null boundary solutions. In the given slicing, the charge expression is integrable because there is no flux, and flux, in fact, is proportional to TLL, and because here TLL vanishes, therefore flux term vanishes, and hence charge variation becomes integrable. Let me add a few more comments on change of slicing, which also was explained by Hussein. If we consider charge variation in the vanishing proton tensor solution phase space, in which mu i's are symmetry generators and QIs are charge densities. In the slicing where we assume that mu i's are state independent, then we can simply integrate this expression and find the charge itself. But we can also consider a generic change of slicing and introduce some other functions, q tilde i's, which are constructed out of qj's and the derivatives. Charge variation can be written as this equation, where mu tilde is related to the symmetry generators by this equation. In the new slicing, we can assume that mu tilde i's are state independent, and then we can integrate variation of charge, and we can find charge itself. But note that QIs do not necessarily form a Lie algebra, and despite the fact that charge variation is invariant under change of slicing, but charge itself is not. One can consider some examples of change of slicing because Hussein gave these examples before. I just want to mention that one thing that here is changed is that in the width part, the width part is changed here due to the appearance of this central term, and instead of having two current plus width algebra in the TMG model, we have two current plus Virasoro algebra, and the same. The similar results can be found here. Now let's consider non-expanding backgrounds because expansion of L with the vector field L is proportional to chi, so we have to set chi equal to 0. The immediate result is that TLL vanishes, and we consistently can set delta chi equal to 0. Therefore, flux vanishes and charges are integrable. We're using a similar Y term, we can render charge integrable. But there exist three classes of solution spaces, which I will address them in the next slides. The first one is a non-vanishing TL phi and T phi. By making a change of slice, one can show that the charge variation can be written as this equation, where phi describe all of functions on the boundary, and transformation laws for these charge densities S tilde, J tilde, and P tilde shows that S tilde and P tilde form a Heisenberg algebra, and J tilde itself again forms a Virasoro algebra. It is also worth mentioning that P tilde charges vanishes when mu goes to infinity, and hence in the pure gravity limit we lose 1/2 of charges, and T transfer and super translations becomes trivial. The next case is vanishing TL phi and non-vanishing T phi. In this case, one of surface charges associated with T transformation vanishes, and the corresponding generators become pure gauge. We can use this transformation to fix the gauge, for example, by setting eta equal to 1, and the charge variation becomes as this equation. And the charge algebra in this case is a U1 Casmodi algebra. The first line at the level 1 by 16 UG, and the Virasoro part, the last line, has a vanishing central charge, or it is simply a Witt algebra. The last case is vanishing TL phi and T phi. And it recovers non-expanding vanishing tensor solution phase space, and the charge algebra is the same as the one in the previous. I have shown in the previous slide. Warp black holes are examples of for non-expanding, non-vanishing proton tensor with TL phi equal to 0. But BTZ black hole is an example for non-expanding vanishing proton tensor case. And one can simply check that black hole entropy is equal to 4 pi times the zero mode charge of wireless scaling, and black hole angular momentum is a minus of zero mode of super rotation charge. So let's recap the results. This work, in fact, is a continuation of studying the null boundary symmetry program started in two previous papers for TMG. This example that we have considered here is the first example in which propagating bulk degree of freedom is turned on. And we have found three tower of charges, namely expansion aspect charge, entropy aspect charge, and angular momentum aspect charge, which label our boundary degrees of freedom. We also found non-zero flux through the null boundary associated with the chiral massive graviton passing through the boundary. And our charts are generic functions over the null boundary. And we show that charge algebra depends on the slicing of solution phase space, and there is a fundamental slicing where we have Heisenberg plus Virasoro algebra. Angular momentum aspect charge satisfy a Virasoro algebra, and entropy aspect charge and expansion aspect charge satisfy a Heisenberg algebra with 1 by 8G as H bar. Also, the algebra, I mean the Heisenberg plus Virasoro algebra, has a direct sum form, and it is invariant on the shift of V. And for further directions could be exploring relation between boundary conditions and variational principle, and finding a rigorous proof of the integrability claim, or extending our results to higher dimensional case, and at the end of the day, quantization of the theory. So thank you for your attention.
Thank you, Hamid, for the nice talk. Can you comment on what happens if you consider other massive theories in 3 dimensions? As you know, we have, for example, new massive gravity, and there are many more of these massive gravity theories. Can you comment on what happens, for example, for these theories instead of topological massive gravity?
In that theories, we also have fluxes, and charges are not integrable in general. But let's say in a new massive gravity, instead of one, we have two propagating degrees of freedom. So the number of propagating degrees of freedom in the bulk will change, but the setup, I guess, can simply apply to that theories too.
And what you would expect for the final result?
I think the result it's definitely one can find fundamental slicing in that theories too. I mean, there should be a slicing where the charge algebra is Heisenberg plus Virasoro algebra.
Did you think that the Virasoro part will have central extension or not?
No, I don't think so, because central charge in the Virasoro part only comes from the gravitational anomaly or directly from non-covariance of the theory, and it is special for the TMG case.
And
The new massive gravity, for instance, it is a covariant theory, and this Virasoro part will be replaced by Witte algebra.
And then do you think that, for example, in NMG will have this Y term? Do we need a Y term there? Or Y term is only for TMG
No,
case?
I think white terms, because in as let me show the white term. White term is proportional to Chern-Simons coupling, and therefore it is there only because the TMG model or its Lagrangian is not invariant under finite diffeomorphisms. And its origin is this capital PC.
Mhm. Okay. Okay, thank you. Thank you for the seminar.